Hi, I'm Jungyu Park. I would like to introduce about content-aware local GAN for photorealistic super resolution. This work is done by my colleague Sang Hyun-son and my advisor Kyung-Mo Lee. Single super resolution in computer vision enhances low resolution image into high resolution ones for better visual quality. Methods have evolved from specialized network with pixel-wise loads to more advanced techniques like perceptual objectives and adversarial training, as in SRGAN. However, some methods overlook local distribution detail by using a global discriminator. Recent super-resolution techniques aim to enhance local details by using local discriminators to distinguish texture in high-resolution and super-resolution images. These discriminators are content-blind, unable to capture diverse local content properties using a single discriminator, which can lead to suboptimal results. Previous methods also fail to differentiate between image categories, resulting in undesirable artifacts in super-resolved images. On this basis, we introduced CalGAN or Content-Aware Local GAN as an innovative adversarial training framework aimed at handling the intricate distribution of natural image based on their content. Instead of relying on a single classifier to comprehend the complexity of natural image manifold, we divide them into smaller subsets according to content. Our approach, a mixture of classifier MOC, effectively manages smaller manifold compared to previous method where features in each group share common properties. Additionally, we propose an efficient routing module and learning strategy to automatically determine suitable feature subsets, eliminating the need for manual assignments. For combining this technique with orthogonal regularization and LD-based approaches, we enhance the separability of learned features, facilitating accurate distribution learning. More specifically, the overall framework of our CalGAN can be depicted as the figure. Our CalGAN eases the burden on the classifier by breaking down complex image distribution into subsets based on content and employing multiple expert classifiers. Each expert classifier is specialized for its corresponding content subsets. To begin with, we use the basic routing module commonly employed in MOE to segment local texture into smaller subsets. This involves combining a convolution module and transforming it into a one-hop vector using Gumbel softmax. However, the straightforward application of this approach can result in certain subsets containing either too little or too much information, leading to a load imbalance problem. This issue, known within the MOE community, can determinately affect the overall performance of the mixture architecture. To address this, we introduced the balancing loss. This loss encourages even distribution of probabilities across subsets by replacing combo softmax with standard softmax. For instance, when the maximum value of softmax distribution R prime becomes smaller, probability values are evenly distributed so that optimizing the loss enforces uniform routing across n subsets. In CalGAN, we enhanced classification by ensuring distinct features for separate classifiers. We achieve this with orthogonal convolutions OI that project feature into a new space. Orthogonal loss optimize the weights O, making sure each OI provides unique independent information. Furthermore, we introduce a distribution-based loss to gather similar information together while separating different information into distinct classes. It consists of two components, between class loss and within class loss. Between class loss increase dissimilarity between different classes, while within class loss minimize the variance within the same class. The final distribution loss is the sum of these two components and effectively adjusts the distance between features. Thus, we define the final loss functions as a combination of the conventional discriminator loss and our newly introduced balancing, orthogonal, and distribution losses. We use visual analysis to illustrate how our routing model functions. In this figure, we show that every pixel in the feature map is assigned to a specific class based on its content, such as sky in the red or detailed texture in blue or black. This visualization confirms that our routing strategy effectively distinguishes image semantics without need for ground truth labels, and the labels are well balanced thanks to our balancing laws. Additionally, in the right figure, we use t-SNP plot to demonstrate that features with different indices form a distinct clusters. This analysis validates that our routing module correctly labels local features based on image context and groups them into the appropriate categories. In the figure, we see the importance of each loss function, Without balancing loads, some classifiers dominate, reducing class diversity. Removing orthogonal loads causes patch-like artifacts as orthogonal ensures category independence. Without distribution loads, objects become indistinguishable, appearing as a noise. In contrast, GAN performs best with all three terms, achieving balanced levels and capturing image details effectively. The right table quantifies our loss function, showing the best result when all three terms are used in GAN. In the left table, we find that patch size 4 works best for SR performance. Smaller patch size and larger patch size result in poor performance due to the classification challenges. Regarding the different classifier numbers, where n is 1, as standard GAN performs the worst. The best results are at n is 12, having the lowest FID score. We demonstrate that GAN works effectively with leading super resolution models including EDSR, RRDB, and SwinIR. Regardless of the baseline model, GAN consistently improves image quality compared to plain GAN approaches. It also competes favorably with LDL, offering sharper and more accurate results. The figure shows the visual comparison between second best model, LDL, and our GAN produce much more visual pleasurable results. Please refer to our paper and supplementary material for more visual comparison. In this work, we propose a novel GAN framework called GAN, which utilizes a mixture of classifiers to address the challenge of handling complex natural image distribution. While previous GAN-based methods learn the distribution of real and fake images unconditionally, our method enables multiple classifiers to learn and distinguish specialized distribution based on its content. Our extensive experiments demonstrate that using multiple classifiers leads to superior handling of complicated natural image distribution and can be extended to other image restoration tasks such as denoising and deblurring. Thank you for listening to the presentation.